Welcome to today's paper reading. Today's paper is titled KN Kolmogorov-Arnold Networks. This paper, titled KN Kolmogorov-Arnold Networks, is a preprint under review. It is authored by Ziming Liu and colleagues from Massachusetts Institute of Technology, California Institute of Technology, and Northeastern University. The abstract introduces Kolmogorov-Arnold Networks, KNs, as an innovative alternative to traditional multilayer perceptrons, MLPs. Unlike MLPs, which have fixed activation functions on nodes, KNs feature learnable activation functions on edges, with all weight parameters replaced by univariate functions modeled as splines. This structural change allows KNs to outperform MLPs in both accuracy and interpretability, particularly in small-scale AI and science tasks. KNs can achieve comparable or better accuracy than larger MLPs in function-fitting tasks, and they exhibit faster neural scaling laws. Additionally, KNs offer enhanced interpretability, enabling intuitive visualization and user interaction. The abstract highlights two examples in mathematics and physics where KNs have proven to be valuable collaborators in helping scientists discover new laws. Overall, KNs present a promising avenue for advancing deep learning models that currently rely heavily on MLPs. Figure 0.1 illustrates the fundamental differences between multilayer perceptrons, MLPs, and Kolmogorov-Arnold networks, KNs. In MLPs, the activation functions are fixed and applied at the nodes, whereas in KNs, the activation functions are learnable and placed on the edges. Notably, KNs do not use linear weights. Instead, each weight parameter is replaced by a univariate function parametrized as a spline. This architectural distinction allows KNs to potentially outperform MLPs in terms of both accuracy and interpretability, especially in small-scale AI plus science tasks. Multilayer perceptrons, MLPs, are foundational in deep learning and are known for their expressive power due to the universal approximation theorem. However, MLPs have significant drawbacks, such as consuming a large number of non-embedding parameters and being less interpretable compared to attention layers. To address these issues, we propose Kolmogorov-Arnold networks, KNs, which are inspired by the Kolmogorov-Arnold representation theorem. Unlike MLPs, KNs place learnable activation functions on edges rather than nodes, resulting in a structure that allows for smaller computation graphs and a combination of the strengths of both splines and MLPs while avoiding their respective weaknesses. Figure 2.1 provides an overview of our proposed Kolmogorov-Arnold networks, KNs, which are named in honor of the two great mathematicians, Andrei Kolmogorov and Vladimir Arnold. These networks are designed to be mathematically sound, accurate, and interpretable, building upon the foundational work of Kolmogorov and Arnold in function representation. The figure highlights the generalization of the original Kolmogorov-Arnold representation to arbitrary widths and depths, positioning KNs within the contemporary landscape of deep learning. This approach revitalizes and contextualizes the original theorem, leveraging extensive empirical experiments to demonstrate its potential for AI and scientific applications due to its accuracy and interpretability. Figure 3.1 illustrates the comparison between Kolmogorov-Arnold networks, KNs, and multilayer perceptrons, MLPs, on 5 toy examples. The results show that KNs can almost saturate the fastest scaling law predicted by our theory, with an exponent alpha equals 4, indicating near-optimal performance. In contrast, MLPs demonstrate slower scaling and quickly reach a plateau, suggesting they struggle to maintain performance improvements with increasing model complexity. Notably, KNs perform particularly well on high-dimensional examples, outperforming MLPs by a significant margin. This highlights the superior scaling properties of KNs compared to MLPs in these scenarios. Table 1 presents a collection of 15 special functions commonly used in mathematics and physics. Each function is associated with its SIPI.special API name, the minimal KN shape required to achieve a test RMSE of less than 10 to the power of -2, and the test RMSE values for both minimal and best KN shapes. Additionally, the table compares the test RMSE of MLPs with that of KNs, highlighting the efficiency and accuracy of KNs in representing these special functions. Table 2 presents the Feynman dataset, which includes various physics equations from Feynman's textbooks. The table compares the performance of 4 types of neural networks: human-constructed KNs, KNs without pruning, KNs with pruning, and MLPs. The results show that auto-discovered KNs are generally smaller than human-constructed ones, indicating that Ka representations can be more efficient. The table also highlights the minimal pruned KN shapes that achieve reasonable loss, and those that achieve the lowest test loss. The method presented in this paper tackles the unsupervised learning problem by transforming it into a supervised learning problem. This is achieved by defining positive samples as feature vectors of real data and negative samples as feature vectors with corrupted features. Feature corruption is performed by randomly permuting each feature across the entire training set to maintain the overall feature distribution. For a synthetic example, a 60 dataset is considered where certain variables are dependent on each other. The preliminary results show that the method can identify these dependencies, although they rely on randomness. In the application to knot theory, supervised learning is used to predict knot invariance. Network attribution methods are employed to identify key invariants, and symbolic regression is used to obtain symbolic forms of these invariants. Table 3 highlights the performance of KNs, kernel attention networks, versus MLPs, multilayer perceptrons, in the signature classification problem. KNs demonstrate superior accuracy, achieving 81.6% with only 200 parameters, compared to MLPs which achieve 78% accuracy but require approximately 300,000 parameters. This significant reduction in parameter count while maintaining or improving accuracy underscores the efficiency and effectiveness of KNs in this classification task. Table 4 presents symbolic formulas of the signature function concerning meridional translation, Ri, and longitudinal translation, lambda. Formula A was manually derived by human scientists, while formulas BF were automatically discovered by KNs. These formulas illustrate a balance between simplicity and accuracy, with KNs demonstrating the ability to discover simpler yet effective formulas, such as formula F which only uses R and lambda. Table 5 presents symbolic formulas for 2 systems, GAM and MAM, alongside their ground truth and KN-discovered counterparts. The table highlights the accuracy of each formula, with GAM-KN auto achieving 98.9% accuracy and MAM-KN auto achieving 97.1% accuracy. This comparison underscores the effectiveness of KN in discovering symbolic forms that closely match the ground truth, facilitating both qualitative and quantitative understanding of the systems. Figure 6.1 provides a decision tree to help determine whether to use KNs, Kolmogorov-Arnold Networks, or MLPs, multilayer perceptrons. The key considerations include the importance of interpretability and accuracy versus the need for fast training. KNs are generally slower to train but offer better interpretability and accuracy, making them suitable for small-scale AI and science problems where these factors are critical. MLPs, on the other hand, are faster to train and may be preferred when speed is a priority. Table 6 provides a list of common functionalities that users may find useful when working with KN, learnable activation networks. These functionalities include training the model on a dataset, plotting the model's output, and pruning the model to remove unnecessary components. Additionally, the table outlines methods for fixing and suggesting symbolic functions for activation, as well as automating the symbolic replacement process and retrieving the symbolic formula of the model. In the experiments, KNs, learnable activation networks, are shown to be perfectly interpretable, as illustrated in Figure 4.1. However, LANs, learnable activation networks, appear much less interpretable, particularly due to the presence of weight matrices. These weight matrices are less readily interpretable than learnable activation functions and introduce too many degrees of freedom, making the activation functions less constrained. This is evident in the synthetic examples shown in figures B.1 and B.2. In the context of LANs, the preliminary results suggest that eliminating linear weight matrices through the use of learnable activations on edges, similar to KNs, is crucial for enhancing interpretability. This approach introduces nonlinearity into the weight matrices, which is believed to be necessary for better interpretability. When it comes to fitting images, implicit neural representations treat images as 2D functions, where the pixel value is a function of its coordinates. This method allows for significant parameter compression while preserving the original image quality. A notable example of this approach is Marin, which demonstrates impressive compression capabilities while maintaining high image quality through the use of a neural network to represent the function f. In this study, the authors proposed the use of multi-layer perceptrons, MLPs, with periodic activation functions to fit the function f. It is noted that it is natural to consider other activation functions, as LANs allow for a variety of such functions. However, the initialization strategy for LAN activations is set to be smooth, similar to SI activations. This approach impacts the function fitting process. Moving forward, there is potential for exploring other activation functions and understanding their impact on model performance, and the potential for improved function fitting. Thank you for watching.